Okay, so we are going to cover lesson 8, or at least the beginning of lesson 8. It is about lines of best fit, and we're going to jump in here on the packet. In this lesson, we examine plots of real-life data and explore how to use the line of best fit. Number 1, this is going to be one of the rare calculator active problems we do this semester. In 1982, drunk drivers were responsible for 25,165 deaths in car accidents. That was 57.3% of all fatalities due to accidents. So of all the different ways that people died in car accidents that year, 57% of them were attributable to drunk driving. The table below shows the percentages of fatalities due to drunk driving for several years. So let's just examine some of the data here. 1982. Like we said, 57% of the deaths in car accidents were due to drunk driving accidents. In 1985, it was 51%. 1988, it was 50%, and we can see what kind of a trend do we notice here in this data? It's going down, right? The percentage of deaths in car accidents that are due to drunk driving has decreased. Yeah. No, these numbers are legit. You can go check out the data there. Yeah. Okay, so the table does give us a sense that the numbers are decreasing, but it doesn't really give us a sense of how they were decreasing. Were they decreasing at the same rate every year, or was it decreasing at like a lot in the beginning and then a little, or the other direction, or was it kind of all over the place? And so another way to think about looking at that data is to draw a graph. And when you draw a graph of a bunch of data points, we just give it a special name. It is called a scatter plot. It's just a plot involving like a scattering of points. And so these are exactly those same points that were up there in the table. One note that the horizontal axis is years since 1980. So all we're doing is calling 1980 t equals 0 instead of putting like literally 1,980 would be, like way down there on the x-axis. So let's just make sure we can identify a couple of points here. We're going to label points A and B. So looking at A, what's the t and what's the y? Looks like 8 and 50. Now I don't want to estimate. I'm going to think it's 8 and 50, but we should be able to see it exactly from the table. Remember, 8 means 8 years from 1980. So that's 1988. What's the data figure in 1988? It's 50. Okay, so we're not estimating. We're like really reading it from the chart. So this is 850. And then point B here, okay, what does it look like the T is? Like maybe 19, and then the Y, yeah, I don't have a lot of confidence. I mean, maybe it's 37, maybe it's 38. But look at the table. What does it say for 99, the last data point? 37. Great. So this is 1937, right? Just grab it from the, 37, the very last one. Okay. So we definitely see that the data is decreasing in nature, but you can also see that it is not decreasing at a constant rate, not decreasing at a linear rate. So for example, you don't need to draw this, but if I just draw line segments connecting every pair of consecutive points, you can see there it was a fairly steep downhill line. That's a fairly shallow downhill line. This one is steeper, although not as steep as the first one. This is a pretty dramatic downhill. This one is pretty shallow, and so is that. And so we can see a lot more information just from the scatter plot than we could with just a list of numbers in the table. Okay, so let's get rid of our line segments and say, can you draw a single line that connects all of those points? No, there is no single line that connects all those points. But you can draw a line that you think is as close as possible to all of those points. And that's what I'm going to ask you to do now. So grab a straight edge. Some of you can grab the bookmarks, maybe grab the green folder. Your goal is to try to draw a line that is as close as possible to all the points. Do not, listen carefully, do not connect 2 of those data points. That is not what I'm asking you to do. I'm asking you to think about all of the data points and try to draw a line that you think is as close as possible to all of them simultaneously. It does not mean connect 2 data points.
So you don't want it to go through?
It's okay if it goes through some of the dots, like if it just randomly goes through the dots, that's okay. But you should not be connecting any particular dots with your line of best fit. Okay, so let's have a look. So here is my line. Does my line hit any of the data points? Does my line hit, like over there, does my line hit that point? Does it really hit that point? I mean, like, yeah, the pixels of the line overlap the pixels of the point, but really, how big is a point supposed to be? Like, we shouldn't even be able to see the point, right? The only reason you can see that one is because I made it, like, enormous. And the same thing with the line, right? How thick is that line really? It's like infinitely thin, right? There's like you shouldn't even really be able to see the line either. So in practice, there's no chance that my line hits that particular point, and yours shouldn't either, but it's okay if it goes very close. And so that right there is my line of best fit. It is going to look different from your line of best fit. We've got like 20 different lines that are drawn here. If I ask you on a test or a quest to draw your best line, I have a wide variety of answers that are full credit, a wide variety of different answers that are full credit. But if you were to draw, for example, this line, I would say that is not a full credit answer. This person did not capture the idea that we want to be close to all of the different points. Another thing that I'm going to take points off for is if you were to do something like connect two particular points. That's only looking at 2 points. I want you to look at all 8 or however many there are there, okay? So don't connect 2 points. Really don't connect any of them. Just try to draw a line that you think is as close as possible to all of the points simultaneously. Okay, so on the next page, we're going to see the right answer. It's kind of wishy-washy for a math teacher to say as close as possible. That is not a very precise phrase, right? But it is a problem that has been solved mathematically. There is one line that is the best fit line that is as close as possible to all of those different points. We're not going to get into the definition for what as close as possible means. Suffice it to say it's out there, and if you take a statistics class, you will see it. But that right there is the absolute best line. We call it the line of best fit. And so that line hopefully is something close to what you drew, but definitely not the same as what you drew, and it's not the same as what I drew. Okay, and because those points are pretty darn close to that line, we can say that the data, the fatalities data, is approximately linearly related or approximately linearly associated. Whereas if you had data points that looked like this, I would not say that that represents a strong linear relationship, right? Lines do not do that. Okay, so moving on here to A. Of all the lines we could draw near the points, the best line, which is graphed above, has a name. We call that graph line the line of best fit, or the least squares regression line if you're being fancy, or more simply the regression line. Okay, part B here says we can use our line to make predictions about the data. Let's use the line of best fit, that's this one, not the one that you drew, to predict the percentage of fatalities due to drunk driving in 1993. 1993. Okay, first we need to know where to find 1993 in this graph. Remember t equals 0 was what year? 1980. So how many years from 1980? 13, right? So 13 is what we're after here. Okay, so t equals 13. And so we go to t equals 13, which is right there. And then we go up to the line, which is right there. And we will just observe that we don't have a data point here, right? 1993 is not in the table, so we are getting information that we did not have before. And then we make our best guess for the percentage at that one point on our line. And so we just jump over here. Again, I've got a range of acceptable and full credit answers. What's our guess here? 43, other guesses? 40, 44 is okay, 42 is okay, but really beyond that, we're kind of pushing it. So we'll just, I'll go in the middle there, and we'll say roughly 43%. Okay, the next part of our process here is to find the equation of that line that's drawn right there. Now you have a lot of practice, including the activity earlier today, where you find the equation of a line. And one of the standard kinds of problems for me to give you, where I ask for the equation of a line, is to start with 2 points. I say, here are the coordinates of 2 points. Tell me the equation of the line that hits them. So that's what you're going to do up here. That's the beginning part of this process. We're trying to pick 2 points that are on the line. Now, just like earlier today, we're looking for points that have nice integer coordinates. And so, for example, if I go over here to this point right here, it looks like that point that's on the diagonal line is pretty darn close to also being on the background grid. And so if that's the case, then I can read off the points. What are the coordinates of that one right there? 16 and 40. I don't think it's exactly 1640, but it's close enough. We're just trying to get some nice numbers that are pretty close to being on the line, okay? And so you can look around and try to find another point that's that has coordinates that are easy to read. Frankly, I don't really see one. I'm just kind of like scanning this diagonal line and looking to see if it goes through the background grid anywhere. And so if you don't see one, you just, you could pick a point that you think is like right in the middle, like halfway in the middle-ish. Ultimately, we're going to need to do an approximation here. There's lots of good answers. Let's just all hone in on this one right here. 20, 35. Where is that? Do we buy that one? 20 and 35. Right over there. So 20, and I made my best attempt at finding one that's halfway. It's definitely not exactly 20, 35, but it's going to be close enough for our purposes. So we're going to find the equation of the line that hits those 2 points right there. Okay? We pick different points, you'll get a different equation of a line, but I've got lots of acceptable full credit answers here, even though they're going to be different answers. But let's all pick those 2 points. One observation before we find the equation of this line. Are either of the points that we picked points from the data table? Right? We didn't pick points that were plotted up there, right? We didn't pick the data points. We shouldn't pick the data points. None of the data points is on the line. You want to pick points on the line. It's really tempting to grab points in the table because you have those. You don't have to do any approximating, but that is the wrong thing to do. Okay, so let's go through the process here. We've got our 2 points. Next step is to find the slope of this line. Typically, it's a change in y over change in x, but we don't have x's and y's in this case. We have t for time and p for percentage. So instead of y, what letter do we have? P is the y, right? Normally it's x and then y. And then delta x, that's really delta t. So we're looking to subtract the percentages over subtract the times. So subtract the percentages, 40 minus 35. And then on the bottom, what order do I need to do? I got to do 16 minus 20. It's okay to do it the other way. So I got 5 on top and negative 4 on the bottom. And I think I said earlier this semester that my preference between decimals and fractions is always fractions because then you don't have to worry about rounding. Like if you write a third, like that's fine, but if you write 0.33, that is not 1/3. But in word problems like this one, it's often easier to think about it in terms of decimals. So this will be kind of the one spot where I break my rule that I have a preference for fractions over decimals. For word problems, I think having decimals is probably easier to think about. Okay, so that right there is our slope. Let's include some units and then we'll write a quick little sentence for what that negative 1.25 means in the context of this problem about driving. Let's get some units up here. The units were the 40 and the 35 on top. That was 40 what? That was 40% and 35%. So clearly upstairs is a percent, even as a decimal, upstairs is a percent. Downstairs, 16 measured what? Years, right? 16 years from 1980, 20 years. So this is negative 4 years. How do I account for that over here? It's not a fraction anymore. It's negative 1.25%. Yeah, per. I have to make it a fraction. You cannot get around the fact that the units here are a fraction. You could write percent per year, and in fact, writing the per instead of the division line is how we're going to write our sentence in a second. So definitely helpful to think of it as a percent per year. Okay, so this means that the accidents due to drunk driving were changing at negative 1.25% per year. changing is not my favorite word. It's a fine generic word, but we're not really taking advantage of the fact that this is a negative number. So can we get rid of the word changing and replace it with what? Decreasing, right? That negative 1.25 is a change of negative 1.25% per year, so that's a decrease. So that'll be our sentence. Let's see. The accidents due to drunk driving were decreasing at 1.25% per year. Those are good words. I mean, like what I've written here is not true. I mean, it wasn't exactly 1.25%, right? We did a lot of approximating here. So good to use those words, but not necessary. Yeah. Okay, so there's our sentence. Now let's go ahead and find the equation of our line. Okay, so we've got our slope, it was negative 1.25, and we just have to go through the process of line equation hunting. So I'll start with my generic y equals mx plus b. I'm going to try to push you out of your comfort zone and tell you not to use x and y because x and y do not appear anywhere in this particular problem. It's t's and p's in some order. What is y? Is p. So p equals m, what is x? T plus b. And just like on this first quest, there was a problem. What was that problem about? It said don't use the letters x and y. So like taxi, was there a taxi fare problem? Who's got the quest handy? Quest handy. There we go. A person starts tracking the height of a bean plant after it reaches 2 centimeters. And then it said, write the equation that relates the height and the number of weeks. And it says, don't use X or Y. Use H for height. Use W for weeks. So this is me trying to push you out of your comfort zone a little bit. And we'll do the same thing right here. Okay, we just calculated negative 1.25. What letter is that? That's the M. So we'll put in P equals negative 1.25 T plus B. Yeah, we got to find the y-intercept, the p-intercept in this case. And so we're going to change the p and the t to some other numbers. You can pick either of the 2 points that we wrote down up above. Let's all be uniform and pick the first one, 16, 40. So let's plug in 16 and 40. Which one is the p? 40 equals negative 1.25 times t is how much at that same point? 16 plus the b. So is that negative 20? Yep. All right, so again, you can type a calculator there if you want. And so then we'll move that over to find b. Add 20 to both sides. We get b is 60. And so then our final equation here is p equals negative 1.25 t plus 60, right? Fair. Here? Yeah, so we just change that b to a 60. Okay, and just a quick reality check because we have the graph in front of us. Does it look like the y-intercept is approximately 60 for that line? Yeah, okay, so that's reasonable, right? But if we got 100, or if we got negative 10, that would indicate there's a problem with the math that we did. Okay, so we've got the equation, so what? Let's see if we can use that equation. So let's rewrite the regression equation right here. So it was p equals negative 1.25 t plus 60. And I said that the actual line of best fit is the one that I graphed there. Well, I used software on the computer to graph it. I used something called GeoGebra. We haven't looked at GeoGebra in this class, have we? So it's a free software. But in any event, that software told me that the real equation is y equals negative 1.19x plus 58.63. That's the exact equation of that line that was drawn. Negative 1.19, what did we get? Negative 1.25, that's not that far, 0.06 off, that's okay. And then the y-intercept, we got 60, it's really 58.63, not so bad. But again, we estimated 2 points on that line. Neither one of them was right. We did our best. Okay, so let's use the equation, the regression line equation, to predict the percent fatalities due to drunk driving in 1993. We've got two equations. We're going to stick with the one that we've created, not the one the computer told us. 1993. Again, we gotta make that translation. Remember, we start the clock at 1980. So how much is t for 1993? T is 13. So we are going to plug t equals 13 into that equation right there. P equals negative 1.25 times 13 plus 60. And somebody with a calculator help us out here.
I got 43.5%.
Okay. Okay, I think that we answered this question on the previous page.
Yeah.
Wasn't there a 1993 problem on the previous page? And we answered this question by looking at the line and just estimating the y-coordinate. What was our answer on the previous page? 43, some people said 44, somebody said 42. 43.75 is really the best approximation we've got at this point. In this case, because 1993 is within the data table, like it's not in there, but it's within the range of years for the data table, we got a fancy word for it. We call it interpolation. When you are in between the extremes of the data, we call it interpolation, as opposed to 2002. What's the last year in the table? 1999, and 2002 is after that, so we're going to have a different word for this. It's going to be extrapolation. If you're outside of the range in the table. So let's try this guy. 2002, again, we translate. P equals, how many years from 1980? 22. And then again, we plug into our same blue equation from the top. P equals negative 1.25 times what number? 22 plus the 60. Just got that one. Yeah.
I got 32.5%.
Okay. Okay, so definitely you're going to expect to see a question like this on the coming quest and on the coming test, where I give you, like I'll give you the scatter plot and I'll say draw your best fit line, pick 2 points that you think are on your line. Don't pick any of my points, pick points that you read from your line, the one that you drew, find the equation of your line, use the equation of your line to do X, Y, or Z, okay? All right. Okay, so we've got about 12 minutes left. You are going to start and not finish the activities that begin on the next page. However far you get here, you'll pick up right there when we come back on Tuesday.